The forward view of your vessel fills with a faint glow as something grows larger against the darkness that surrounds you on this long crossing between galaxies. That something is the Andromeda Galaxy, a vast island of stars that has slowly emerged from the void as your spacecraft nears the end of an endless journey through the emptiest region of space humans could ever experience. You are now deep within intergalactic space, where almost nothing exists for millions of light years in any direction. The Milky Way has faded behind you into a spiral smudge, no larger than your outstretched hand held at arm's length against the rear observation window. Ahead, the galaxy you are approaching spreads wider with each passing moment. A tilted disk of light that will soon become your entire sky. Andromeda contains roughly 1 trillion stars, and from this distance, they blend together into a continuous glow that reveals the galaxy's structure in ways no view from Earth could ever provide. The central bulge shines brightest, a concentrated sphere of golden light marking the heart where your journey will eventually take you over the course of this long night. Spiral arms wind outward from that center, alternating bands of stellar light and darker dust lanes that wrap around the disk in graceful curves extending for tens of thousands of light years. 2 smaller companion galaxies float nearby, fuzzy patches of light called M32 and M110 that orbit this larger structure like moons orbiting a planet. You are listening to the Drowsy Astronaut, and tonight we travel together across 2.5 million light years to enter another galaxy entirely. This journey will carry us from the outermost reaches of Andromeda's halo through spiral arms and ancient stellar populations until we arrive at the supermassive black hole beating silently at its heart. If you enjoy these slow voyages through the cosmos, consider sharing where you are listening from tonight in the comments below. And if you'd like to continue exploring the universe together, you're always welcome to join us on future journeys by liking or subscribing. The stars ahead are waiting for you now, patiently, as you drift closer to a galaxy that has existed for billions of years before this moment. The intergalactic space surrounding your vessel contains almost nothing at all, perhaps 1 atom of hydrogen for every cubic meter of volume. Emptier than any vacuum humans have ever created in laboratories on Earth. This void between galaxies represents the loneliest environment in the entire universe. Regions where light travels for millions of years without encountering any matter to scatter or absorb its energy. Your spacecraft crosses this emptiness at speeds that would seem impossible by any normal measure, covering distances that light itself requires years to traverse in fractions of that time. The technology enabling this journey belongs to imagination, but the destination ahead is real, a place that exists right now as you rest wherever you are tonight. Andromeda's disk appears tilted from your approach angle, presenting itself at roughly 77 degrees from face on, which allows you to see both the spiral structure and some of the disk's thickness simultaneously. This viewing angle reveals how thin the disk actually is compared to its enormous width. A structure spanning over 220,000 light years across, but only a few thousand light years thick at most points. The tilt also lets you observe the dust lanes more clearly. Those dark ribbons that cut across the brighter stellar glow and mark regions where dense clouds of gas and microscopic particles block the light from stars behind them. From directly face-on, the spiral structure would appear even more dramatic. But this tilted view shows the galaxy as a three-dimensional object rather than a flat disk. The central bulge dominates the galaxy's core, a spherical concentration of ancient stars that formed early in Andromeda's history when the universe itself was still relatively young. This bulge glows with a warm golden-orange color, different from the bluer tints visible in portions of the spiral arms, where younger, hotter stars continue forming today. The color difference tells a story about stellar populations, about which stars formed when, and how their temperatures affect the light they emit across the spectrum. Ancient stars have had billions of years to cool and redden, while young stars burn hot and blue for their comparatively brief lifetimes before exhausting their fuel. The spiral arms winding outward from the central bulge represent density waves moving through the disk, regions where matter concentrates and triggers star formation as the galaxy rotates. These arms are not solid structures, but patterns that persist while individual stars move through them over millions of years, like traffic jams on a highway that remain in place while individual cars pass through. The bright blue concentrations visible within the arms mark regions where new stars are being born right now, stellar nurseries where gravity collapses clouds of gas into the fusion engines that light the universe. The darker lanes between and within the arms contain the raw materials for future stars, dust and gas that will eventually participate in the next generation of stellar birth. Your vessel continues its approach, and with each passing moment, details emerge that were invisible just seconds before, the galaxy revealing itself layer by layer as distance decreases. Individual regions within the spiral arms become distinguishable from the general glow. Brighter knots and darker patches that indicate the complexity waiting to be explored as you move closer. The satellite galaxy M32 appears as a compact bright ellipse near the disk, a smaller companion containing perhaps 3 billion stars that orbits within Andromeda's gravitational embrace. M110 drifts farther out, a more diffuse and extended companion that shows evidence of gravitational interaction with the larger galaxy it accompanies through space. The journey from the Milky Way to this point would have taken light itself approximately 2.5 million years to complete, meaning the light reaching your eyes right now departed Andromeda when early humans were just beginning to walk the plains of Africa. This delay between emission and observation applies to everything astronomers study in the distant universe, making every telescope a time machine that reveals the past rather than the present. The Andromeda you are approaching exists as it was long ago. Though the timescale of galactic change is so slow that 2.5 million years makes little practical difference to the overall structure you observe. Stars are born and die within that span, but the galaxy itself continues rotating and evolving at a pace that human lifetimes cannot perceive. The void behind you stretches back toward home, toward the Milky Way that grows smaller with each moment of forward progress through the darkness between islands of light. Our home galaxy appears remarkably similar to Andromeda from this external vantage point, a spiral structure with arms and bulge and halo that would look almost like a mirror image if you could see them side by side. The two galaxies are approaching each other at approximately 110 kilometers per second, drawn together by mutual gravitational attraction across the gulf that currently separates them. In roughly 4 to 5 billion years, these two island universes will begin merging into a single larger structure, their stars intermingling over hundreds of millions of years. The scale of what lies ahead requires a moment to appreciate fully, even as the view continues growing larger and more detailed with your ongoing approach. 1 trillion stars occupy the structure before you, each one a sun in its own right, many likely hosting planets of their own in systems that have never been observed by anyone from Earth. The light from all those stars combines into the glow, filling your forward view, a glow that represents more suns than any human could ever count, even if they devoted their entire lifetime to the task. This is another galaxy, complete and entire, a separate city of stars that has existed for over 10 billion years in the darkness of intergalactic space. The halo surrounding the visible disk extends far beyond what the eye can easily perceive. A sparse population of ancient stars and globular clusters that occupy a vast spherical region around the concentrated disk and bulge. This halo represents the first region you will enter as your vessel approaches close enough to pass through the galaxy's outermost boundary, though the exact edge of a galaxy is difficult to define precisely. Stars become progressively more scattered at greater distances from the center, density decreasing gradually rather than ending at any sharp boundary line. Your crossing from intergalactic void to galactic halo will happen smoothly, marked more by the increasing frequency of passing stars than by any visible edge. The dust lanes crossing the disk appear from here as dark ribbons winding through the brighter stellar glow, features that will become far more prominent once you enter the spiral arms themselves. These lanes contain microscopic particles of carbon and silicon, and other elements forged in the hearts of earlier generations of stars, particles that accumulate in the denser regions of the spiral pattern. The dust absorbs and scatters light from stars behind it, creating the dark appearance that contrasts with the bright concentrations of unobscured stellar populations on either side. Within those dusty regions, new stars are forming right now, hidden from direct view by the very material from which they are condensing. The angle of approach you have taken will carry you down toward the disk from above the galactic plane, allowing extended observation of the spiral structure before you enter the disk itself. This trajectory passes first through the diffuse halo, then through whatever globular clusters happen to lie along your path, before descending into the spiral arms that wind around the disk. The journey inward from there will carry you through both active star-forming regions and quieter interarm spaces, eventually reaching the crowded inner disk and central bulge. The supermassive black hole at the very center waits at the end of this long voyage, an invisible presence that shapes everything around it through gravitational influence alone. Andromeda grows larger still, and the time approaches when individual stars will begin appearing as distinct points of light rather than blending into the continuous galactic glow. The outermost halo stars drift through space at enormous distances from their nearest neighbors, separated by light years of emptiness that make even our sparse local neighborhood around the sun seem crowded by comparison. These ancient wanderers follow long, looping orbits around the galactic center, taking billions of years to complete single circuits through the vast volume they occupy. Some of them have orbited dozens of times since their formation, while others are still completing their first slow journey around the galaxy that holds them. The passage from empty intergalactic space into the galaxy's gravitational domain happens without any visible marker, a transition defined by physics rather than by any boundary you could observe directly. At some distance from the center, the galaxy's gravitational pull becomes the dominant influence on the motion of objects within that region, defining membership in the structure. Your vessel has likely already crossed this invisible boundary, having entered the region where Andromeda's mass shapes trajectories rather than the random motions of the intergalactic void. The journey into the galaxy proper now begins, with the first ancient stars of the outer halo soon to appear around your vessel. The forward view fills with soft galactic light as your approach continues, the darkness of the void giving way to the gentle illumination of 1 trillion distant suns, blended into a unified glow. This light has traveled for millions of years to reach this point in space. Photons that departed their source stars during ages when human civilization did not yet exist on Earth. The colors within the glow tell stories about the stars producing them, about temperatures and compositions and ages that vary across the galactic structure. Blue-white regions mark the youngest, hottest stars, while the golden central bulge reveals the ancient populations that formed when the galaxy itself was still assembling from smaller fragments. The final stretches of intergalactic void pass beneath your vessel as the halo boundary approaches, the transition from empty space to populated galaxy now imminent with each passing moment. Ahead, the first scattered stars of the outer halo wait to be encountered, ancient travelers that mark the outermost extent of the structure you are entering. The journey into Andromeda begins in earnest as these first stellar neighbors appear around your vessel. Points of orange and red light that glow with the steady patience of suns that have burned for billions of years. The galaxy welcomes you into its embrace as the crossing from void to halo completes itself in the silence of space. The first star of Andromeda's halo drifts past your vessel at a distance that still measures in light years, a solitary red giant burning steadily in the darkness that surrounds it on all sides. This ancient sun has existed for perhaps 10 or 11 billion years, having formed when the galaxy itself was still young and the universe contained far fewer heavy elements than it does today. No other stars appear nearby, the emptiness between halo neighbors, so vast that this red giant seems to float alone in its own private pocket of space. You have entered the outermost region of another galaxy, and the loneliness of this place speaks to the immense scale of the structure you are now exploring. The halo extends in all directions around the main disk, visible ahead, a roughly spherical distribution of ancient stars that were among the first to form in this galaxy's long history. These stars follow orbits very different from the circular paths of disk stars, instead tracing long elliptical loops that carry them far from the galactic center before gravity pulls them back for another close passage. Some halo stars travel so far from the center that completing a single orbit requires billions of years, timescales that approach a significant fraction of the universe's total age. The star, drifting past your viewport right now, might be on one of those immense journeys currently passing through the outer reaches of its orbit before beginning the long fall back toward the galactic core. The color of this first halo star tells you something about its nature, that deep orange-red glow, indicating a sun that has exhausted the hydrogen fuel in its core and expanded into its giant phase. Stars like this, one began their lives much smaller and hotter, burning steadily for billions of years before running low on the fuel that powers their fusion reactions. When a star's core hydrogen depletes, the core contracts while the outer layers expand and cool, creating the red giant appearance that characterizes many of the ancient stars visible in galactic halos. This star will eventually shed its outer layers entirely, leaving behind a dense white dwarf core that will cool slowly over timescales longer than the current age of the universe. Another star appears in the distance as your vessel continues deeper into the halo. This one even fainter than the first, perhaps a smaller and cooler red dwarf that has burned steadily since its formation. Red dwarfs are the most common type of star in any galaxy, far outnumbering the brighter giants and main sequence stars that dominate visual observations. Their faintness makes them difficult to detect at great distances, but they exist in enormous numbers throughout the halo and disk of every galaxy. This particular red dwarf might have several trillion years of fuel remaining, enough to outlast the galaxy itself as it continues its slow nuclear burning in the darkness between more prominent neighbors. The space between halo stars remains remarkably empty, containing only the sparse gas and dust that pervades all galactic regions and the invisible dark matter that constitutes most of the halo's actual mass. Dark matter provides the gravitational scaffolding that holds galaxies together, an unseen component that interacts with normal matter only through gravity without emitting or absorbing any form of light. Scientists estimate that dark matter outweighs normal matter in most galaxies by factors of 5 or 6 to 1, meaning the halo around you contains far more invisible mass than the stars you can actually observe. Your vessel passes through this dark matter without any direct awareness of its presence, the particles flowing through solid matter without interaction. The main disk of Andromeda remains visible ahead and below your position, that concentration of spiral arms and central bulge now appearing as a structure rather than a single unified glow. Details that were invisible from greater distance now emerge clearly. Individual regions of brightness and darkness that mark the complex geography of the galactic plane. The descent toward that disk will continue for some time, with much of the halo still remaining to cross before you reach the denser stellar populations of the spiral arms. For now, the halo surrounds you with its ancient scattered stars, a sparse environment where neighbors remain rare and encounters rarer still. A faint, fuzzy sphere appears in the distance, noticeably brighter than the scattered individual stars, and showing definite extent rather than appearing as a mere point of light against the darkness. This is a globular cluster, one of hundreds that orbit within Andromeda's halo, a dense concentration of ancient stars that formed together early in the galaxy's history. From this distance, the cluster appears as a soft glow, but closer approach will reveal hundreds of thousands of individual stars packed into a volume perhaps 100 light-years across. Your trajectory may carry you near or through such a cluster, providing an opportunity to experience one of the most ancient types of stellar structures that galaxies contain. The halo stars surrounding you differ significantly from the stars in the disk visible below, their chemical composition reflecting the conditions that existed when they formed over 10 billion years ago. The early universe contained primarily hydrogen and helium, with only trace amounts of the heavier elements that later generations of stars would produce through fusion and distribute through supernova explosions. Halo stars formed from this relatively pristine material, incorporating very little of the carbon, oxygen, iron, and other elements that make up rocky planets and biological life. Their spectra reveal this ancient heritage, showing elemental abundances that serve as cosmic fossils, preserving information about conditions in the early universe. The orbital motions of halo stars also differ from disk stars, moving in random directions rather than the organized rotation that characterizes the flattened disk population below your position. Disk stars orbit the galactic center in roughly the same direction, creating the rotating spiral structure visible from your current vantage point above the galactic plane. Halo stars show no such coordination, each following its own path on trajectories that may be inclined at any angle to the disk, or even retrograde to the general rotation. This random motion reflects the chaotic early history of galaxy formation, when smaller proto-galactic fragments merged together from many different directions before the disk could settle into organized rotation. Many of the stars currently occupying this halo did not form within Andromeda at all. Instead, originating in smaller galaxies that were later absorbed and disrupted by the larger structure's gravitational pull. Galaxies grow in part by cannibalizing their smaller neighbors, tearing apart dwarf galaxies that wander too close and incorporating their stars into the growing halo population. The disruption process can take hundreds of millions of years, during which the captured stars spread out along their orbital paths into stellar streams that eventually blend with the general halo population. Some of the scattered stars drifting past your viewport might be immigrants from galaxies that no longer exist as separate structures. The darkness between stars dominates your surroundings, despite having entered the galaxy proper, the halo's extreme sparseness making it barely distinguishable from the intergalactic void you recently left behind. The difference lies in potential rather than immediate experience. The knowledge that stellar neighbors exist somewhere in this darkness, even if few are currently visible from your particular position. The disk below represents the promise of denser regions ahead, regions where stars appear in far greater numbers and the character of space itself seems to change with their concentrated presence. For now, the halo's ancient wanderers accompany your journey in their scattered solitude, each one a sun that has burned for longer than Earth has existed. Another globular cluster appears ahead, this one closer to your trajectory than the first, and beginning to resolve into individual stellar points around its concentrated core. The cluster contains perhaps 500,000 stars packed into a space that would fit comfortably between our sun and its nearest neighbor in the Milky Way's local neighborhood. This extreme density represents a very different environment than the sparse halo surrounding it, a pocket of stellar crowding that has persisted for over 10 billion years. Your path toward the galactic disk may carry you through or near this cluster, offering a brief passage through one of the most remarkable structures in the ancient galaxy. The gravitational dynamics within a globular cluster create constant stellar interactions over the billions of years the cluster has existed, gradually sorting stars by mass and ejecting some members entirely into the surrounding halo. Heavier stars tend to sink toward the cluster's core, while lighter stars drift toward the outskirts, a process called mass segregation that operates over millions of years of repeated gravitational encounters. Some stars have been ejected entirely, flung out of the cluster by close passages with other members and now wandering the halo as solitary travelers. The cluster ahead has been evolving through these processes since it formed, its current structure reflecting billions of years of gravitational interaction among its crowded stellar population. The light from globular cluster stars blends into a unified glow at the cluster's dense core, where individual members become impossible to distinguish against the background of their neighbors. Only at the cluster's outer edges do stars appear sufficiently separated to observe individually, their ancient orange and red colors indicating the low temperatures of stars that have burned for most of cosmic history. The brightest stars within any globular cluster are the red giants, evolved stars whose expanded atmospheres make them hundreds of times more luminous than the smaller dwarf stars that actually dominate the cluster's population by number. The giants stand out like beacons among their fainter companions, marking the cluster's position even from great distances. Your approach to the globular cluster continues as the disk of Andromeda spreads wider in the background, the two structures occupying different regions of your forward view as you descend through the halo. The cluster grows larger and more detailed, while the disk reveals new complexity, both destinations offering different types of exploration as this journey proceeds. The choice to pass through the cluster will provide an experience unavailable in the sparser halo regions, a brief immersion in ancient stellar density before the long descent through more modern stellar populations toward the galactic heart. The halo continues its slow parade of scattered ancient stars as you travel, each one representing a nuclear furnace that has burned steadily for longer than our entire solar system has existed around its yellow parent star. These stars have witnessed the entire history of planet formation, biological evolution, and human civilization occurring in the Milky Way 2.5 million light-years away. They have no knowledge of those events, of course, simply continuing their patient fusion reactions as gravity holds their enormous masses together against the outward pressure of the energy they generate. Their existence predates almost everything humans consider ancient, their origins reaching back toward the beginning of structure formation in the universe itself. The passage through the halo approaches its midpoint as the globular cluster fills more of the forward view, its ancient stars now clearly visible as individual points surrounding the concentrated core glow. The transition from halo to cluster will happen gradually as stellar density increases, the space between stars shrinking from light years to fractions of light years as you enter the cluster's gravitational domain. This will be a brief passage through crowded space before returning to the sparser environments beyond, a glimpse of what stellar concentration looked like in the early universe when such clusters formed. The cluster awaits your arrival with the patience of 10 billion years of existence, its stars continuing their ancient orbital dance around the common center of mass. The globular cluster expands to fill your forward view as your vessel approaches its outer boundary. Individual stars, now clearly visible as distinct orange and red points surrounding the brighter, concentrated core. The transition from halo to cluster happens gradually, marked by the increasing frequency of stars appearing around you, rather than any sharp boundary edge. What was emptiness, with occasional stellar visitors, becomes space with neighbors, then space with crowds, as the cluster's density asserts itself around your trajectory. The oldest stars in this galaxy surround you now, ancient suns that formed together from the same primordial gas cloud over 10 billion years ago. The stars at the cluster's edge orbit relatively slowly around the common center of mass, their paths carrying them on long, elliptical journeys that take them far from the dense core before gravity pulls them back for another close passage. These outer members represent the cluster's most loosely bound population, stars whose orbital energy places them near the threshold of escape from the gravitational well that holds the structure together. Some stars at these distances will eventually break free entirely, gradually leaking away from the cluster over billions of years until only the tightly bound core remains. The cluster slowly evaporates through this process, though the timescales involved exceed the current age of the universe many times over. The color palette surrounding you consists almost entirely of oranges and reds, the characteristic tints of ancient low-mass stars that have burned steadily since the universe was young. Blue and white stars are notably absent, having exhausted their fuel and ended their lives billions of years ago when the cluster was still in its relative youth. The brightest stars you observe are red giants, older stars that have expanded and cooled after depleting the hydrogen in their cores through billions of years of fusion reactions. These giants provide most of the cluster's visual luminosity, despite representing only a small fraction of the total stellar population by number. Deeper into the cluster, the stellar density increases noticeably with each moment of forward progress through the ancient structure surrounding your vessel. Stars that appeared as distant points now drift past, at closer range, their orange and red light contributing to a growing ambient glow that fills space itself with soft illumination. The crowding has not yet reached its maximum, the true core still ahead, where stars pack together so tightly that distinguishing individuals becomes difficult against the background of their neighbors. This intermediate region offers clear views of individual cluster members, while providing a sense of the density that characterizes these remarkable ancient structures. Some of the stars surrounding you may host planets of their own, worlds that formed from the sparse, heavy elements available in the early universe and have orbited their parent stars for over 10 billion years. These hypothetical planets would be very different from Earth, lacking the abundant metals that characterize younger worlds in more chemically enriched environments. Rocky planets around globular cluster stars might contain less iron, less silicon, fewer of the elements that make up the bulk of terrestrial worlds in our own solar system. Life as we know it might find such environments challenging, though the true requirements for biology remain uncertain enough to leave many possibilities open. The gravitational environment within the cluster differs significantly from the sparse halo you recently departed. With stellar neighbors now close enough to exert measurable gravitational influence on each other's motions. Over millions of years, these gravitational interactions accumulate into significant orbital changes, with stars being gradually deflected from their paths by close passages with other cluster members. The process resembles a very slow game of gravitational billiards, where each interaction transfers small amounts of energy and momentum between the participants. Some stars gain energy through these encounters and drift toward the cluster outskirts, while others lose energy and sink deeper toward the dense core. The cluster's core becomes visible ahead as a region of significantly increased brightness, where stellar density climbs to levels that seem almost impossibly crowded compared to the emptiness of intergalactic space you crossed to reach this place. Thousands of stars occupy a volume here that would contain perhaps 1 or 2 stars in the neighborhood around our Sun, a concentration that results from billions of years of gravitational focusing toward the cluster's center of mass. The core has likely collapsed partially during the cluster's long history, with gravitational interactions driving the central regions to ever higher densities over timescales of billions of years. This process may eventually be reversed by binary star interactions that inject energy back into the core, creating a slow oscillation between collapse and expansion. Individual stars within the core region become difficult to distinguish as your approach continues, their combined light blending into a continuous glow that hides the discrete nature of the stellar population. The brightest red giants still stand out as distinct points against this background, their luminosities hundreds of times greater than the smaller dwarf stars that dominate the population by sheer numbers. These giants serve as markers within the core, providing reference points against the undifferentiated glow of their less luminous neighbors. The experience of passing through this region involves immersion in ancient starlight, rather than observation of individual stellar neighbors. The cluster has survived for over 10 billion years through a delicate gravitational balance that continues maintaining its coherence against the tidal forces that the galaxy exerts upon it. Andromeda's gravity tries to pull the cluster apart with each passage through the denser inner regions of the galaxy, stretching and distorting the structure in ways that eventually strip away the most loosely bound outer members. The cluster compensates by contracting its core, concentrating mass more tightly at the center, where gravitational binding is strongest and resistance to tidal disruption greatest. This ongoing battle between internal gravity and external tides has shaped the cluster's current structure, determining which stars remain bound and which have been lost to the surrounding halo. The passage through the cluster's densest region happens relatively quickly, despite the slower apparent pace of travel. The concentrated core occupying only a small fraction of the cluster's total volume, even as it contains much of the gravitationally bound mass. Stars drift past on all sides, their ancient light filling your viewport with the warm orange-red glow that characterizes these evolved populations. No young stars remain here to provide the blue-white brilliance that marks active star formation regions elsewhere in the galaxy. This is a stellar retirement community, populated entirely by the long-lived survivors of an ancient stellar generation. Beyond the core, the stellar density begins decreasing again as you pass through the cluster's far side, the crowded environment giving way gradually to the sparser conditions of the outer regions and eventually the halo beyond. The transition mirrors your approach in reverse, with stars becoming less frequent and the spaces between them expanding with each moment of outward progress. The cluster recedes behind you as a concentrated glow against the backdrop of the galactic disk, still waiting ahead, its ancient population continuing their gravitational dance as they have for billions of years. Your passage through this structure was brief on cosmic timescales, a moment of human experience within a context of astronomical permanence. The halo surrounds you again as the cluster fades into the distance, its scattered ancient stars appearing once more as solitary points rather than the crowded neighbors of the cluster environment. The contrast emphasizes how unusual globular clusters are within the general galactic structure. Dense islands of stellar concentration, floating in seas of relative emptiness. The cluster you just traversed will continue orbiting Andromeda's center for billions of years to come. Its stars maintaining their ancient community against the gradual processes of evaporation and tidal stripping. Other clusters orbit elsewhere in the halo, some closer to the galactic disk and some farther out in the distant reaches you crossed earlier. The galactic disk has grown notably larger and more detailed during your passage through the cluster, the spiral structure now appearing clearly, with its alternating bright arms and dark dust lanes winding around the central bulge. Your descent toward that disk continues with each moment, bringing the denser stellar populations of the spiral arms gradually closer. The environment ahead will differ dramatically from the ancient uniformity of the halo and its globular clusters, offering regions of active star formation, colorful nebulae, and the mixed stellar populations that characterize galactic disks throughout the universe. The transition from halo to disk represents a boundary between the galaxy's past and present, between stars that formed at the universe's beginning and stars that are being born right now. The final stretches of the halo pass beneath your vessel as the disk boundary approaches, the ancient stars thinning out as you near the transition zone, where halo and disk populations begin to intermingle. The experience ahead will include younger stars, denser clouds, and more active stellar environments than anything the halo has offered during your traverse of this region. The spiral arms wait below, their blue-white concentrations marking the locations where gas clouds collapse into new stellar generations. The journey from ancient to modern, from the galaxy's first stars to its newest, happens through this transition from halo to disk that your descent now approaches with each passing moment of forward motion through the darkness. The disk spreads wide beneath your position, its structure now visible as something you could enter rather than merely observe from great distance above the galactic plane. The spiral arms curve around the central bulge in patterns that will soon surround you, rather than appearing as features on a distant surface below. The approach angle carries you toward one of these arms, a region where gas and dust concentrate and new stars emerge from collapsing clouds in ongoing cycles of stellar birth. The experience of entering that arm will differ from anything the sparse halo has provided, offering immersion in the active processes that continue shaping this galaxy after 10 billion years of stellar evolution. The disk of Andromeda spreads beneath your vessel like an enormous rotating landscape of light and shadow, its spiral structure laid out in full view as you continue your descent from the halo above. The perspective reveals details invisible from greater distance, individual features within the arms becoming distinguishable from the general glow that characterizes the disk when viewed from millions of light years away. Dark dust lanes wind through brighter stellar concentrations, the contrast between light and dark creating the spiral pattern that defines galaxies of this type throughout the universe. This view from above shows the disk as a structure you will soon enter, a vast environment that stretches for over 200,000 light-years and contains the bulk of Andromeda's stellar population. The spiral arms curve outward from the central bulge in great sweeping arcs, each arm representing a density wave that moves through the disk and triggers star formation wherever it concentrates gas and dust to critical levels. These arms are not solid structures, but patterns that persist while stars and gas flow through them, like standing waves in a river that maintain their shape while water constantly passes. Stars that form within an arm eventually drift away as they complete their orbits around the galactic center, but the arm pattern remains, continuously triggering new stellar generations from the gas that flows into its concentrated regions. The arms you see below will look essentially similar in appearance millions of years from now, even though the specific stars within them will have changed. The bright blue-white concentrations within the arms mark regions where star formation is most active, places where massive young stars have recently emerged from their birth clouds and illuminate their surroundings with intense radiation. These hot young stars will not last long by cosmic standards, burning through their fuel in just millions of years before exploding as supernovae that scatter their enriched material back into the interstellar medium. The blue regions appear bright precisely because these massive stars pour out enormous amounts of light during their brief lifetimes, outshining their longer-lived neighbors many thousands of times over. From your position above the disk, these stellar nurseries appear as pearls strung along the spiral arm threads. The darker regions between and within the arms contain the raw materials from which new stars will eventually form. Clouds of gas and microscopic dust particles that absorb and scatter the light from stars behind them. These dark lanes are not empty, but rather filled with matter that will participate in future stellar generations. Hydrogen molecules and carbon grains and frozen water that drift through space, awaiting gravitational collapse. The contrast between dark dust and bright stars creates the visual definition of the spiral pattern, each arm outlined by the interplay of light and shadow across the galactic disk. Your descent will eventually carry you into these regions where the view changes from looking at clouds to being surrounded by them. The central bulge dominates the inner portion of your view, a concentrated, spherical population of ancient stars that formed early in the galaxy's history and now orbit within the inner regions of the disk. This bulge appears golden orange in color, reflecting the low surface temperatures of the old red giant and dwarf stars that dominate its population. The contrast with the bluer spiral arms emphasizes the different stellar populations that coexist within a single galactic structure. Ancient and young, sharing the same gravitational home, but occupying different regions and following different orbital patterns. Your eventual journey through the bulge will immerse you in these ancient populations, but first, the spiral arm descent awaits with its younger stars and active environments. The disk rotates too slowly for any motion to be perceptible during your observation, but the physics of that rotation shapes everything you see below your current position. Stars closer to the center orbit faster than stars farther out, a differential rotation that winds up the spiral pattern over hundreds of millions of years. Without some mechanism to maintain them, the spiral arms would wind themselves tighter and tighter until they disappeared entirely after just a few galactic rotations. The density wave theory explains their persistence, proposing that the arms represent patterns moving through the disk rather than material features composed of the same stars over time. Your approach angle will carry you into one of the spiral arms rather than into the quieter interarm regions, providing an immediate experience of the most active stellar environments the disk has to offer. The arm ahead contains all the features characteristic of such regions throughout the galaxy: young stars and old, dense clouds and scattered dust, nebulae glowing with the energy of their embedded stellar populations. The transition from halo to arm will happen gradually as you descend through the disk's upper boundary layer, but eventually, the arm environment will surround you completely with its mix of stellar generations and active processes. The thickness of the disk appears minimal compared to its enormous horizontal extent, a flattened structure only a few thousand light-years thick at most points, while spanning over 200,000 light-years from edge to edge. This flatness results from the rotation of the disk population, orbital motion that supports the stars against gravitational collapse in the horizontal direction, while allowing the structure to compress in the vertical direction, where no such support exists. The halo stars above you are not flattened in this way because their random orbital orientations provide support against collapse in all directions simultaneously. The disk below represents a more organized population, stars that follow similar orbital paths around the galactic center. The position of the Sun's equivalent location in this galaxy would fall somewhere in the outer disk, roughly 60,000 light-years from the center, in a region between spiral arms where stellar density remains moderate and relatively constant. From such a position, the view toward the galactic center would be partially obscured by intervening dust, while outward views would show the relatively sparse stellar populations of the outer disk and distant halo. Your current position above the disk allows a clearer view of the overall structure than any observer within the disk could ever obtain. The spiral pattern and central bulge visible in their entirety without obstruction. The transition zone, where halo and disk populations intermingle, appears below as you continue descending, a region where the random motions of halo stars give way to the more organized rotation of the disk population. This boundary is not sharp but gradual, with characteristics of both populations blending together over a range of heights above and below the disk midplane. Your passage through this zone will mark the true entrance into the disk environment, leaving behind the ancient halo stars and entering the mixed populations where stellar ages span the full range from just formed to nearly as old as the universe itself. Individual stars in the disk begin appearing more frequently as your descent continues. Disk population members joining the occasional halo stars that still drift past at this intermediate height above the galactic midplane. The disk stars show more variety in their colors than the uniformly ancient halo population, ranging from red dwarfs and giants to yellow stars like the Sun, to the blue-white giants that mark the youngest stellar generations. This diversity reflects the ongoing star formation that has continued throughout the disk's history, each generation adding new stars, while previous generations continue burning through their fuel at rates determined by their masses. The spiral arm ahead grows larger and more detailed as you approach the disk's upper boundary, its complex structure resolving from the simple bright band visible at distance into a textured environment of stars, clouds, and illuminated nebulae. The arm represents your entry point into the disk proper, a region where you will experience the active processes that continue shaping this galaxy after billions of years of stellar evolution. The descent from halo through disk boundary into spiral arm will complete the first major phase of this journey, transitioning from the ancient outer reaches of the galaxy into the living heart where new stars continue emerging from the raw material of space. The dust within the arm becomes visible as discrete structures rather than a general darkening, individual cloud complexes appearing as silhouettes against the stellar background or as glowing nebulae where internal stars illuminate the surrounding material. These clouds range in size, from small, dense cores that might form single stars to enormous complexes spanning hundreds of light years that could generate entire stellar associations. The variety of cloud types and illumination conditions creates a complex visual environment, very different from the uniform emptiness of the halo you have been crossing. Your immersion in this environment approaches with each moment of continued descent. The final stretch of descent carries you through the disk boundary layer into the spiral arm itself, the transition marked by increasing stellar density and the appearance of the first large dust cloud complexes around your trajectory. The arm environment surrounds you now, rather than appearing as a feature below, its mixed populations and active processes replacing the quiet, ancient character of the halo that has accompanied you until this point. The journey through the disk begins here, with the first spiral arm passage providing introduction to the environment that dominates the middle portion of this long voyage toward the galactic center. The spiral arm surrounds your vessel with a richness of stellar content that makes the sparse halo seem like empty space by comparison. Stars appearing in every direction at varying distances, while clouds of gas and dust drift through the visible field. The transition from halo to arm happened gradually, but now the arm environment dominates completely, its mixed populations creating a visual complexity impossible in the ancient outer regions of the galaxy. Young blue stars burn brilliantly in the distance, their intense light illuminating nearby gas clouds that glow with colors ranging from red to blue, depending on their temperatures and the wavelengths they emit. This is the living portion of the galaxy, where star formation continues today and will continue for billions of years into the future. A stellar nursery appears ahead as a glowing cloud complex, hydrogen gas illuminated from within by the hot young stars that have recently emerged from the collapsing material that gave them birth. The cloud glows primarily in shades of red and pink, the characteristic color of ionized hydrogen that has been energized by ultraviolet radiation from the embedded stellar population. Tendrils of darker dust weave through the brighter regions, dense lanes where the concentration of particles blocks the light from whatever lies behind. This nursery is actively forming new stars right now, gravity pulling together clumps of gas that will eventually collapse into fusion engines that light the universe. The process of star formation begins when a region within a molecular cloud becomes dense enough for its own gravity to overcome the pressure that normally keeps gas clouds from collapsing. This can happen through various triggers, including the compression caused by density waves moving through the disk, shock waves from nearby supernova explosions, or the gravitational influence of nearby massive objects. Once collapse begins, the process accelerates as the contracting material heats up and radiates away energy, allowing further contraction until temperatures and pressures in the core become sufficient to ignite nuclear fusion. A new star is born when this fusion begins, converting hydrogen to helium and releasing the energy that makes stars shine. The stars emerging from this particular nursery span a range of masses, from red dwarfs smaller than the Sun that will burn for trillions of years, to blue giants many times more massive that will exhaust their fuel within just a few million years. The mass of a forming star depends on the details of its collapse, including how much material was available in the initial clump and how the collapse proceeded without fragmenting into multiple smaller cores. Massive stars form rarely because the conditions favoring their creation are less common, while low-mass red dwarfs form abundantly because smaller clumps of gas can collapse successfully under a wider range of conditions. The result is a population dominated by small, faint stars with occasional larger, brighter members. The blue giants visible within the arm will end their lives dramatically within cosmically brief timeframes. Their enormous masses driving fusion reactions at rates that deplete their fuel far faster than smaller stars manage. When a massive star exhausts its core fuel, the resulting core collapse triggers a supernova explosion that briefly outshines the entire galaxy, scattering material enriched with heavy elements into the surrounding interstellar medium. This enriched material will eventually participate in future generations of star formation, becoming part of the gas that collapses into new stellar systems, with planets containing the elements necessary for complex chemistry and potentially life. Every atom in your body heavier than helium was forged in such stellar cores and distributed by such explosions. Your vessel passes near the outer edge of the glowing nursery complex, close enough to observe individual bright stars within the illuminated gas, but not so close as to enter the densest cloud regions, where visual observation would become obscured. The young stars here have emerged from their birth cocoons relatively recently, by cosmic standards, perhaps within the last few million years of an existence that may continue for much longer, depending on their masses. The most massive members have already begun affecting their environment, their intense radiation carving cavities in the surrounding gas, and their powerful stellar winds pushing material outward from their positions. Beyond the nursery, other features of the spiral arm environment become visible as your journey continues through this active region of the galactic disk. Open star clusters appear scattered through the arm, groups of stars that formed together from single cloud complexes and remain loosely associated through their similar trajectories. These clusters are younger than the ancient globular cluster you traversed in the halo, typically containing hundreds or thousands of stars rather than hundreds of thousands, and showing the mixed colors that indicate ongoing stellar evolution rather than the uniformly ancient populations of globular systems. An open cluster might remain coherent for hundreds of millions of years before gravitational interactions with the disk environment gradually disperse its members. An open cluster drifts past at moderate distance, its young stellar population creating a concentration of bright points against the general stellar background of the arm. This cluster probably formed from a single molecular cloud collapse within the last few 100 million years, its stars having traveled together through space, while remaining loosely bound by their mutual gravitational attraction. The brightest members are blue-white giants that will not survive another 100 million years, while the fainter yellow and red stars will continue burning for billions of years after their brilliant siblings have exploded as supernovae. The cluster as a whole will eventually disperse, its stars spreading out along similar orbital paths until they become indistinguishable from the general disk population. The dust pervading the spiral arm creates subtle visual effects, throughout your passage, slightly reddening the light from more distant stars as their photons scatter through the accumulated particles between source and observer. This reddening effect makes distant stars appear slightly more orange than they actually are, similar to how Earth's atmosphere reddens the light from the setting sun by scattering away the bluer wavelengths. The effect accumulates with distance, making very distant stars appear significantly redder and fainter than they would if the dust were not present. Astronomers must account for this interstellar extinction when measuring the true properties of distant stellar populations. Nebulae of various types appear throughout the arm, each representing different physical processes and different stages of stellar and interstellar evolution within this active region. Emission nebulae glow with the light of excited gas ionized by nearby hot stars. Reflection nebulae shine with scattered starlight bouncing off dust grains. Dark nebulae appear as silhouettes against brighter backgrounds. Some nebulae represent material expelled by dying stars, planetary nebulae or supernova remnants that gradually mix with the interstellar medium and contribute to future stellar generations. The variety of nebula types creates a complex visual environment very different from the uniform ancient character of the halo you departed. The stellar density within the arm exceeds that of the interarm regions you will cross later, though the difference is subtle compared to the extreme contrast between arm and halo populations. Perhaps twice or 3 times as many stars occupy a given volume within the arm compared to the spaces between arms, a concentration that reflects the density wave pattern that defines the spiral structure. This concentration brings gas clouds close enough together and compresses them sufficiently to trigger the star formation that makes the arms visually prominent, creating the bright stellar populations that define the spiral pattern from great distances. The arm extends both ahead and behind along your trajectory, its curved structure wrapping around the galaxy toward the center and outward toward the sparse outer disk in opposite directions. Your path through the arm will eventually carry you out the other side into an interarm region where the stellar density decreases and the active processes of star formation become less prominent. For now, the arm environment surrounds you with its complexity, its mix of young and old stars, its clouds and clusters, and glowing nebulae. The experience differs dramatically from anything the halo offered during your traverse of that ancient region. The raw materials for future stars drift through space around you as clouds of molecular hydrogen, carbon monoxide, and other compounds that will eventually participate in gravitational collapse and stellar ignition. These clouds remain cold and dark, except where embedded stars heat their surroundings, their temperatures hovering just tens of degrees above absolute zero, where molecules can survive without being torn apart by thermal energy. The darkness and cold protect the molecules that will become the next generation of stars, preserving the raw materials in forms that can participate in the collapse and fusion processes that create new stellar systems. The passage through this first spiral arm continues as your trajectory carries you deeper into the disk, angling gradually toward the galactic center that remains your ultimate destination, still many light years and several structural transitions ahead. The arm will eventually give way to an interarm region, which will give way to another arm, the spiral pattern repeating as you spiral inward toward the dense central bulge and the black hole hidden at the galaxy's heart. Each region will offer its own characteristics and visual environment. The variety of the disk contrasting with the uniform ancient character of the halo you have now left behind. The density of stars and clouds begins thinning as your vessel passes through the trailing edge of the spiral arm, the concentrated stellar populations giving way to the sparser environment of the interarm region that lies beyond. The transition happens gradually over a span of perhaps 1,000 light years, the bright blue giants and glowing nebulae becoming less frequent until they fade from view entirely behind your trajectory. The interarm region represents a different character of the galactic disk, quieter and less active than the arms, dominated by older stellar populations that have had time to drift away from their birth regions. The contrast with the arm you just traversed emphasizes how the spiral pattern concentrates the most dramatic features of galactic structure into relatively narrow bands. The stars surrounding you now show predominantly yellow and orange colors, main sequence and giant stars that have burned steadily for billions of years since their formation, in arms that no longer exist at their current locations. These stars formed in spiral arms long ago, but their orbital motions carried them away from those birth regions as the density wave pattern moved through the disk at a different rate than the stellar orbits themselves. A star might spend only a fraction of its orbit within a spiral arm, with most of its existence passing through the quieter interarm regions where you now travel. The experience of being between arms offers a very different perspective than the active environment of the arm itself. The interstellar medium in this region contains less gas and dust than the spiral arm environment, allowing clearer views across greater distances without the absorption and scattering that characterized your passage through the previous dense cloud complexes. Stars appear slightly bluer and brighter than they did within the arm, their light reaching you without passing through as much intervening material that would redden and dim their signals. This relative clarity reveals the structure of the disk more plainly, the next spiral arm visible ahead as a brighter band curving across your forward view, while the arm you departed recedes into a similar band behind. The galaxy's spiral pattern appears laid out before you in the interarm clarity. Star formation occurs rarely in interarm regions because the gas density remains too low to trigger gravitational collapse at the rates characteristic of the concentrated arm environments. An occasional star might form where local conditions happen to favor collapse, but the systematic generation of new stellar populations depends on the compression and concentration that spiral arms provide. The stars you observe here formed elsewhere and wandered into this region through their orbital motions, a population of immigrants rather than natives to this particular location in the galactic disk. The next spiral arm will present another opportunity to observe active star formation before you continue toward the inner galaxy. The quieter character of the interarm region provides a contrast that makes the spiral pattern meaningful, defining the arms as concentrations against this background of relative emptiness. Without the interarm regions, the spiral structure would be invisible, the entire disk appearing as a uniform distribution of stellar populations, without the bright and dark variations that create the spiral visual effect. The pattern requires both components, the concentrated arms and the sparse interarms, to create the structure that characterizes spiral galaxies throughout the universe. Your passage through this quieter region helps complete the picture of how such galaxies are organized. An ancient red giant drifts past at moderate distance, its expanded orange atmosphere glowing with the light of a star that has exhausted its core hydrogen and entered the final phases of its existence. This star may have formed 5 or 6 billion years ago in a spiral arm that has since wound around the galaxy many times. Its position in the interarm region reflecting billions of years of orbital motion since that distant origin. The star will eventually shed its outer layers and collapse to a white dwarf, leaving behind a dense remnant that will cool over timescales longer than the current age of the universe. For now, it burns through its remaining fuel in the relative isolation of the interarm environment. The view toward the galactic center has become clearer as dust concentrations decreased during your transition from arm to interarm space. The central bulge now visible in greater detail than at any previous point in this journey. The golden-orange glow of the bulge dominates the forward view, a spherical concentration of ancient stars that marks your eventual destination through many more transitions of galactic structure. The nuclear region at the very center remains hidden at this distance, but the bulge itself presents a clear target that grows larger with each moment of continued progress toward the inner galaxy. The gravitational dynamics in the interarm region differ subtly from those within the arms, with lower concentrations of mass creating less complex gravitational environments for the stars that pass through. The orbital motions remain dominated by the overall galactic potential, the combined gravity of the central regions that keeps all disk stars following roughly circular paths around the galactic center. Perturbations from the spiral arm density waves create the variations in stellar paths that lead to the concentration and dispersal of populations across the disk structure. These variations accumulate over millions of years of orbital motion, gradually mixing stellar populations across the disk. Looking back along your trajectory, the spiral arm you departed appears as a bright band decorated with blue concentrations and threaded with dark dust lanes, the active environment receding into the distance, while the interarm environment extends ahead toward the next concentration. The transition from one arm to the next involves crossing this quieter region, where the drama of star formation gives way to the steady burning of established stellar populations. Your path continues through this transition zone toward the next arm encounter, the spiral pattern creating a rhythm of density and emptiness that repeats across the galactic disk. The stellar population in the interarm region includes representatives of all the generations that have formed throughout the galaxy's history, from ancient stars that formed when the disk was young, to relatively recent additions that emerged from arms within the last billion years. This mixing of generations creates a population with a wide range of ages, compositions, and eventual fates, all sharing this region of space through the coincidence of their current orbital phases. Some stars here will survive for trillions of years, while others have only millions or billions of years remaining before they exhaust their fuel and begin their final evolutionary stages. The next spiral arm becomes increasingly prominent ahead as you continue crossing the interarm region. Its bright stellar populations and dark dust lanes beginning to show individual features rather than blending into a single concentrated band. This arm will provide another passage through the active environment of star formation and young stellar populations before the journey continues toward the increasingly dense regions of the inner disk. The transition from interarm to arm will happen gradually, the stellar density increasing and the characteristic features of arm environments beginning to appear around your trajectory. The relative emptiness of the interarm crossing allows time for reflection on the variety you have already encountered during this voyage. From the sparse, ancient halo to the crowded globular cluster, to the active spiral arm, to this quieter, intermediate region. Each environment offers its own character and its own perspective on the structure of this immense galaxy, the variety emerging from the different physical processes that created and maintain each region. The journey ahead will continue this variety, passing through additional arms and inter-arm regions before reaching the different environment of the central bulge, and eventually the extreme conditions near the supermassive black hole at the galaxy's heart. The disk continues its imperceptible rotation around you. Stars and gas orbiting the galactic center at velocities of hundreds of kilometers per second that appear stationary at the scales on which this journey proceeds. A complete rotation at this distance from the center requires approximately 250 million years, meaning the disk has completed perhaps 40 full rotations since the galaxy formed. Each rotation carries stars and gas through the spiral pattern multiple times, with passages through arms triggering star formation that adds new stellar generations to the disk population. The process has continued for billions of years and will continue for billions more as the galaxy maintains its slow gravitational dance. The approach to the next spiral arm accelerates as the interarm region narrows toward its conclusion, the bright band ahead resolving into individual features, while stellar density begins climbing back toward arm values. The transition will carry you back into the environment of active star formation, young stellar populations, and complex nebula structures that characterized your first arm passage. Each arm offers its own specific features while sharing the general characteristics that define spiral arm environments, providing both familiarity and novelty as the voyage continues through the disk toward the inner galaxy. The second spiral arm surrounds your vessel with renewed stellar density and active cloud complexes. The inter-arm crossing completed and the characteristic arm environment once again filling the view in all directions. This arm shares the general features of the first arm you traversed: young blue stars scattered among older populations, glowing nebulae marking sites of recent star formation, dark dust lanes threading through the brighter regions. The specific features differ in their details, each arm containing its own particular arrangements of stars and clouds that result from the local history of stellar birth and death within this region of the galactic disk. Your trajectory through this arm carries you on a path that angles gradually toward the galactic center. Each light year of progress bringing you closer to the dense inner regions where the disk structure begins giving way to the spheroidal central bulge. The spiral arms become less distinct in the inner galaxy, the clear separation between arm and inter-arm fading as stellar density increases regardless of position within the spiral pattern. This arm may represent one of the last clearly defined spiral structures you encounter before the environment transitions to the more uniform inner disk that surrounds the bulge. The central bulge has grown notably larger in your forward view during the passages through arms and inter-arm regions, its golden orange glow now dominating the inner portion of the visible field. The bulge contains perhaps a quarter of the galaxy's total stellar mass, concentrated into a relatively small volume compared to the extended disk, creating an environment of significantly higher stellar density than anything the disk itself can offer. Your eventual passage through this bulge will immerse you in ancient stellar populations, far more dense than the ARM environment currently surrounding you. A large molecular cloud complex appears ahead along your trajectory, a dark structure silhouetted against the stellar background where dust and gas concentrate in densities sufficient to block the light from stars behind. This cloud may contain enough mass to form thousands of stars if triggered into collapse by the compression of passing density waves or shock fronts from nearby stellar explosions. For now, it drifts through the ARM in cold darkness. Its interior temperatures just tens of degrees above absolute zero, where molecules remain stable and await the gravitational processes that could transform them into stellar systems. The cloud's darkness stands in stark contrast to the glowing emission nebulae visible elsewhere in the ARM, the difference reflecting whether stellar energy sources exist within the cloud to illuminate its contents. Dark clouds like this one have not yet formed the stars that would light them from within, or the stars that have formed remain too deeply embedded for their light to escape through the obscuring material. Eventually, some portion of this cloud will collapse, igniting new stars whose energy will begin illuminating the remaining gas and transforming the dark cloud into a glowing stellar nursery. Passing around the edge of the cloud complex, your view reveals the intricate structure of dust lanes and gas concentrations that characterize these potential stellar nurseries, awaiting their gravitational destiny. Filaments and wisps of material extend from the main cloud body, some of them dense enough that they might already be collapsing towards star formation on timescales of millions of years. The cloud has existed in more or less its current form for perhaps 10 million years, drifting through the ARM while slowly evolving through the processes that will eventually transform portions of it into stellar systems. The stellar density in this inner spiral ARM exceeds that of the outer ARM you traversed earlier, reflecting the general increase in star concentration that occurs as you move closer to the galactic center. More stars occupy each cubic light-year of space here than in the outer disk, a gradient that will continue steepening as you approach the inner disk, and eventually the central bulge. The increased density creates a richer visual environment, more stellar neighbors visible at any given moment as you travel through the ARM toward its inner edge. The mixing of stellar populations within the ARM creates a complex tapestry of ages and evolutionary states, from young stars still surrounded by remnants of their birth material, to ancient red giants that have wandered into this region after billions of years of orbital motion. Some stars here are experiencing their first passage through a spiral ARM since forming, while others have passed through dozens of ARMs during their long existence. The ARM environment treats all these populations similarly, concentrating them along with the gas and dust that constitutes the raw material for future stellar generations. The transition from disk to bulge lies ahead, but still distant, perhaps 15 or 20,000 light-years of continued progress through disk structure before the environment changes fundamentally. The inner disk will present increasing stellar density and decreasing clarity of the spiral pattern. The concentrated ARM structures of the outer disk giving way to a more uniform distribution as you approach the central regions. The bulge beyond that represents yet another environment, ancient and dense, leading ultimately to the nuclear region and the black hole that anchors the entire galactic structure. A young stellar association passes at moderate distance, a loose grouping of hot blue stars that formed together from a single cloud complex within the last few million years. These stars remain near their birth site, not yet having drifted apart through the differences in orbital velocity that will eventually disperse them across the disk. The brightest members illuminate nearby gas, creating small emission regions that glow with the characteristic pink of ionized hydrogen. This association will disperse over the next 100 million years, its members becoming indistinguishable from the general disk population. The approach to the inner edge of this spiral arm brings changes in the visual environment, the distinct features of arm structure beginning to blur into the more uniform conditions of the inner disk that lies beyond. The clear contrast between arm and interarm fades as stellar density increases regardless of position within the weakening spiral pattern. The inner galaxy presenting a different organizational character than the well-defined outer disk. This transition marks the beginning of the final approach to the central regions, where the bulge and its ancient populations await your arrival. The spiral arms have provided immersion in the active processes that continue shaping this galaxy. Star formation and stellar evolution, creating new generations, while old stars complete their cycles and return material to the interstellar medium. These processes will continue for billions of years as the galaxy maintains its slow rotation and its spiral pattern continues triggering stellar birth in the disk. Your passage through these arms has witnessed a snapshot of this ongoing activity, a moment in a process that spans timescales far beyond any human experience. The inner disk approaches as the spiral arm structure fades behind your trajectory. The environment ahead, showing the increased stellar density and reduced structural definition that characterizes the regions surrounding the central bulge. The variety of the outer disk gives way to the more uniform inner environment, preparation for the eventual transition from disk to bulge that will immerse you in the ancient stellar populations concentrated at the galaxy's heart. The journey continues toward these denser regions, with each moment of forward progress through the evolving galactic structure. The central bulge fills more of the forward view than ever before, its golden glow now clearly distinguishable as a distinct structure rather than merely the brightest part of a continuous disk. The approach to this ancient concentration of stars will carry you through the remaining inner disk before the transition from rotating disk population to spheroidal bulge population marks the final major structural change before the nuclear region itself. The black hole at the center awaits at the end of this long voyage, drawing everything toward itself through gravitational influence that shapes the entire galaxy. The inner disk surrounds your vessel, with stellar density notably higher than anything the outer disk provided. Stars appearing more frequently and at closer apparent distances as you travel through this concentrated region approaching the central bulge. The spiral arm structure has faded almost entirely from view. The clear distinction between arms and interarm regions, giving way to a more uniform distribution of stellar populations across this inner portion of the galactic disk. The environment here represents a transition zone between the organized rotation of the disk and the more random motions of the spheroidal bulge that rises ahead, mixing characteristics of both populations as they intermingle at this structural boundary. The central bulge now dominates your forward view, a massive concentration of ancient stars that appears as a wall of golden-orange light, rising from the disk plane into a spheroidal structure extending above and below the flattened disk. This bulge contains perhaps 25 billion solar masses of stellar material, much of it in the form of old red giant and dwarf stars that have burned steadily for 10 billion years or more. The color of the bulge reflects these ancient populations, the low surface temperatures of evolved and long-lived stars, creating the warm golden tones that distinguish the bulge from the bluer disk regions behind you. The transition from disk to bulge involves more than just a change in stellar density, representing a fundamental shift in the types of stellar orbits and the history of the populations you will encounter as you enter this ancient structure. Disk stars follow relatively circular paths around the galactic center, all rotating in roughly the same direction with similar orbital inclinations. Bulge stars show far more variety in their orbital characteristics, some on radial plunges toward and away from the center, others on highly inclined paths that carry them far above and below the disk plane. The organized rotation of the disk giving way to more chaotic motion patterns. The boundary between disk and bulge cannot be drawn precisely, the two populations intermingling across a broad transition zone rather than meeting at any sharp dividing line. Disk stars wander into bulge regions, while bulge stars sometimes pass through the disk plane, the gravitational dynamics of the inner galaxy creating complex mixing between populations that formed under different conditions at different times. Your passage through this transition will be gradual, the character of your surroundings shifting slowly from disk-dominated to bulge-dominated as you continue toward the galactic center. The ancient stellar populations of the bulge formed early in the galaxy's history, before the disk had fully assembled and settled into its current organized rotation pattern. Some bulge stars may have originated in the violent merger events that characterized the early assembly of the galaxy, formed in smaller protogalactic fragments that later combined to create the structure visible today. Others formed during the initial collapse of the primordial gas cloud that became Andromeda, igniting their fusion reactions over 10 billion years ago, in an era when the universe itself was still young and galaxies were still taking their current forms. The colors of bulge stars indicate their great ages, the orange and red tints reflecting the low surface temperatures of stars that have had billions of years to evolve away from the hotter, bluer states of their youth. Blue stars are absent here because any massive blue stars that might have formed in the bulge exhausted their fuel and ended their lives billions of years ago, leaving behind only the long-lived, lower-mass stars that could survive to the present day. The most luminous stars visible are red giants, evolved stars whose expanded atmospheres make them temporarily brighter than their smaller, longer-lived companions. The first true bulge stars begin appearing around your vessel as you cross into the inner boundary of the transition zone, their orbital characteristics revealing them as members of this ancient population rather than disk stars temporarily passing through. These stars move on paths that differ from the organized disk rotation, their velocities and directions showing the random orientations characteristic of the spheroidal bulge structure. The mixing of disk and bulge populations will continue for some distance, but the bulge component steadily increases as a fraction of the stars surrounding your trajectory. The dust and gas that characterize the disk environment have largely disappeared in this transition to bulge regions, swept clean by the lack of density wave compression and the different gravitational dynamics of the inner galaxy. Star formation ended in the bulge long ago, when the available gas was consumed by the initial stellar generations, leaving behind the evolved populations you now observe without the raw materials for creating new stars. The absence of dust creates clearer sight lines through the bulge than were possible in the dusty disk arms, allowing views across greater distances despite the increased stellar density. The nuclear region at the very center of the galaxy remains hidden behind the bulge stars that will surround you for the next phase of this journey. The supermassive black hole, lying many light years distant through the ancient stellar populations you are now entering. The approach to that ultimate destination will proceed through the deepening bulge environment, where stellar density continues increasing and the gravitational influence of the central mass becomes ever more apparent in the motions of stars around you. The view backward toward the disk reveals the full extent of the structure you have traversed. Spiral arms and interarm regions spread across your rear field of view as a flattened band of light decorated with the features you explored during your passage. The disk continues its slow rotation, the stars within it completing orbits that take hundreds of millions of years, while participating in the density wave patterns that maintain the spiral structure. Your journey through that disk has concluded as you enter the ancient bulge that represents the galaxy's gravitational heart. The bulge deepens around you with each moment of forward progress. The transition from disk-dominated to bulge-dominated environment now essentially complete, as the ancient stellar populations fill every direction of your surrounding view. The golden orange glow of aged stars creates an ambient illumination that differs in character from the mixed light of the disk, a warm, ancient radiance that reflects 10 billion years of stellar evolution. This is the inner sanctum of the galaxy, the region where most of the gravitational mass concentrates, and where the most ancient surviving stars continue their patient orbital dance around the center. The stellar density here exceeds the disk by factors of tens or hundreds, depending on exactly how far toward the center you have progressed at any given moment. The sky has transformed from the scattered points of the outer regions to a crowded field where stars appear in every direction at varying distances, some close enough that their light contributes noticeably to the ambient illumination filling space itself. The experience of being surrounded by so many ancient suns creates a different feeling than the disk provided, an immersion in concentrated stellar light that intensifies with each light year of continued inward progress. The orbital velocities of bulge stars reveal the gravitational mass concentrated at the center. Stars moving faster here than disk stars at greater distances, because they feel the pull of more concentrated mass at smaller radii. These velocities will continue increasing as you approach the nuclear region, where stars orbit so rapidly that their motion might become perceptible over human observational timescales. The central black hole contributes to this gravitational pull, its 100 million or more solar masses adding to the stellar mass that accelerates everything in its vicinity. The bulge extends ahead for thousands of light years of continued travel toward the nuclear concentration at the very center. This ancient stellar population providing the environment for the next major phase of your journey through the galaxy. The density will continue increasing, the stellar crowding intensifying until the nuclear star cluster appears as a distinct concentration within the already dense bulge. The black hole waits at the center of that cluster, invisible itself, but shaping everything around it through gravitational influence that extends across the entire galaxy. The bulge has closed completely around your vessel now, its ancient stellar populations filling every direction of view with orange and red light from suns that have burned since the universe was young. The disk has vanished from direct observation, hidden by the dense concentration of bulge stars that surround your position, deep within this spheroidal structure at the galaxy's heart. The environment here differs fundamentally from anything the outer galaxy offered. The sparse emptiness of the halo and the active variety of the disk arms, replaced by a uniform sea of ancient stellar light that intensifies with each moment of continued inward progress. The stellar density surrounding you has climbed to levels that seem almost impossibly crowded compared to the emptiness of intergalactic space, where this journey began so long ago in the darkness between galaxies. Stars appear by the hundreds in every direction, their combined light creating an ambient glow that fills space itself with illumination rather than leaving the background dark between visible points. The nearest stars pass close enough that distinguishing them as individual objects presents no difficulty. Each one an ancient sun that has maintained its nuclear fires for 10 billion years or more, while orbiting within this central concentration. The colors of the bulge population show remarkable uniformity. The orange and red tints of aged low-mass stars dominating to the near exclusion of the bluer colors that marked younger stellar generations in the disk. This uniformity reflects the ancient character of the population. All these stars having formed during the same general era of cosmic history, when the galaxy was assembling from primordial material. The most massive stars that formed alongside these survivors exhausted their fuel and ended their lives billions of years ago, leaving behind only the patient, long-lived stars that could endure to the present day. Some stars within the bulge show slightly different characteristics than their neighbors, hints of different formation histories or different chemical compositions that distinguish populations formed under varying conditions during the galaxy's early assembly. Astronomers studying our own Milky Way's bulge have identified multiple stellar populations with subtly different properties, evidence of the complex merger events and assembly processes that created these central concentrations. Andromeda's bulge likely shows similar complexity beneath its overall ancient character. Populations that formed in different proto-galactic fragments, now thoroughly mixed by billions of years of orbital motion. The gravitational environment within the bulge continues strengthening as your inward progress carries you closer to the concentrated mass at the galactic center. Stars moving faster on their orbits as they respond to the increased gravitational pull from smaller radii. These faster orbital motions reflect the fundamental physics that governs all gravitationally bound systems. Objects moving more quickly when they orbit closer to the source of gravitational attraction. The black hole at the center contributes 100 million or more solar masses to this central concentration. Its gravitational influence reaching outward through the bulge to affect the motions of stars throughout this region. The view in any direction reveals a similar scene of crowded ancient stars. The spheroidal symmetry of the bulge, creating uniform conditions regardless of which way you look from your current position deep within the structure. This uniformity contrasts with the disk environment, where spiral arms and interarm regions created distinct zones with different characteristics depending on position and viewing direction. The bulge offers no such variation, only the steady increase in stellar density as you approach the nuclear concentration where the journey will reach its climax. A particularly bright red giant passes at moderate distance, its expanded atmosphere glowing more brilliantly than the smaller dwarf stars that dominate the bulge population by sheer numbers. This star may have only millions of years remaining before it sheds its outer layers and collapses to a white dwarf, ending a stellar life that has spanned perhaps 10 billion years since its formation during the galaxy's youth. For now, it burns through its remaining fuel at the accelerated rate characteristic of giant stars, contributing its luminous presence to the ancient glow of the surrounding bulge. The nuclear region at the very center becomes distinguishable ahead as a region of even greater brightness, a concentration within the concentration that marks the innermost structure of the galactic core. This nuclear region contains perhaps 1 million stars within a volume just a few light-years across. Stellar density climbed to extreme levels that approach the conditions within globular clusters, but maintained by the gravitational influence of the central black hole rather than by the star's own mutual gravity. Your approach to this region continues with each moment of forward progress through the deepening bulge. The stellar motions around you have become measurably rapid at these distances from the center, orbital velocities climbing as the gravitational well deepens toward the concentrated mass ahead. Stars that take millions of years to complete orbits in the outer galaxy here complete circuits in centuries or millennia, accelerated by the gravitational pull that intensifies with decreasing distance from the center. The black hole's contribution to this acceleration becomes more significant as you approach. Its compact mass adding to the stellar mass in creating the gravitational field that governs all motion in this region. The ambient temperature of space itself has increased subtly in these inner regions. The accumulated radiation from so many stellar sources, creating thermal conditions slightly elevated above the near absolute zero temperatures of intergalactic space. This thermal environment reflects the concentration of energy sources, the combined output of billions of stars, creating a background radiation field that pervades the bulge unlike anything possible in the sparser outer regions. Your vessel passes through this sea of ancient light, absorbing radiation from stars in every direction that contribute their photons to the general illumination. The transition to the nuclear region approaches as the stellar density continues its steady climb, the already crowded bulge giving way to the even more extreme concentration that immediately surrounds the central black hole. This transition represents the final major structural change before the journey reaches its destination. The approach to the gravitational heart, where 100 million solar masses concentrate into a volume smaller than our solar system. The nuclear star cluster emerges ahead as a distinct brightening against the general bulge glow, the innermost sanctum of this ancient galaxy. The bulge has provided immersion in what the early galaxy was like, its ancient populations preserving conditions and characteristics that reflect formation processes active when the universe was still young. These stars witnessed the assembly of the galactic disk, the many rotations that wound up the spiral pattern, the ongoing star formation that continues today in regions you have now left far behind. They will continue their patient orbits for billions of years into the future, outlasting our sun and eventually the sun's own galaxy as the Milky Way and Andromeda merge into a single combined structure. The final approach to the nuclear region now dominates the forward view. The distinct concentration of the nuclear star cluster, visible ahead as your trajectory carries you toward the extreme environment surrounding the supermassive black hole at the galaxy's center. The nuclear region of Andromeda rises ahead as a distinct concentration of stellar light, brighter than the already dense bulge surrounding it, marking the innermost structure of this ancient galaxy, where the supermassive black hole exerts its gravitational dominance. Your approach to this region has carried you through progressively denser environments, from the sparse halo through the varied disk, to the uniform ancient bulge, each transition bringing new characteristics, while steadily increasing the stellar concentration around your vessel. The nuclear region represents the final intensification before the black hole itself, the last zone of normal stellar matter before gravitational effects become extreme. The stellar density here exceeds anything you have previously encountered during this long voyage. Millions of stars concentrated into a volume just tens of light years across, compared to the 100,000 light-year extent of the full disk you traversed to reach this point. Stars appear so numerous that counting individuals becomes impossible, the combined light creating a brilliant glow that fills space with illumination far exceeding the conditions in any outer region. This is the most crowded stellar environment in the entire galaxy, the gravitational well of the central black hole having concentrated ancient stars into this extreme configuration over billions of years of orbital evolution. The motions of stars in this region reveal the gravitational influence of the central mass more clearly than anywhere else in the galaxy. Orbital velocities climbing to hundreds or thousands of kilometers per second, as the black hole's pull accelerates everything within its reach. Some stars here complete full orbits around the galactic center in just decades or centuries, timescales short enough that their motion could be directly observed through patient astronomical monitoring over human lifetimes. The fastest stars approach the event horizon closely before swinging back out into the nuclear cluster, their trajectories bent sharply by the extreme gravitational curvature near the black hole. The black hole itself remains invisible, of course, defined by the absence of light rather than its presence, a region of space-time from which nothing that enters can ever return to the external universe. Its mass has been estimated at roughly 100 million to 230 million times the mass of our Sun, a concentration of gravitational influence that shapes the entire inner galaxy through its pull on surrounding matter. The event horizon, the boundary beyond which escape becomes impossible, measures perhaps several light hours across for a black hole of this mass, a sphere of gravitational no return, hidden at the center of the brilliant nuclear cluster. The environment immediately surrounding the black hole may include some gas and dust currently falling toward the event horizon. Though Andromeda's central black hole appears relatively quiet compared to the violently active nuclei of some other galaxies, when a supermassive black hole is actively feeding on large amounts of infalling material, that material heats to extreme temperatures as it spirals inward, creating brilliant accretion disks and powerful jets visible across the entire universe. Andromeda's black hole currently lacks such dramatic activity, instead sitting relatively quiescent within its nuclear star cluster, while slowly consuming whatever stray material wanders close enough to be captured. The stars closest to the black hole follow orbits that would seem impossibly fast by the standards of the outer galaxy, their paths carrying them around the central mass in periods of years rather than the hundreds of millions of years required for a single orbit at the Sun's equivalent distance from the galactic center. These innermost stars experience tidal forces from the black hole's gravitational gradient. The pull on their near sides stronger than the pull on their far sides by amounts that could theoretically tear apart objects passing too close. Stars survive because their internal gravity holds them together against these tidal stresses, but the stretching forces become extreme as distances to the event horizon decrease. The view of the nuclear cluster from your current approach angle shows its roughly spherical structure, stars distributed in all directions around the central concentration, without the flattening characteristic of disk populations, orbiting in organized rotation. These stars move in all orientations, some plunging radially toward the center before swinging back out, others on more circular orbits at various inclinations to any reference plane. The three-dimensional chaos of these orbital orientations creates a complex gravitational environment where close encounters between stars happen more frequently than anywhere else in the galaxy. Surprisingly, some of the stars within the nuclear cluster appear young. Blue giants that should have exhausted their fuel billions of years ago, if they formed with the ancient bulge population surrounding this region. The presence of these young stars near the hostile environment of a supermassive black hole presents a puzzle that astronomers continue working to understand, as the extreme conditions would seem to inhibit rather than encourage the processes of star formation. Some theories suggest these stars formed from gas that fell toward the center and accumulated into a disk, where gravitational collapse could occur, while others propose they migrated inward from formation sites farther out in the galaxy. The approach to the innermost regions continues as your vessel carries you deeper into the nuclear concentration. The stellar density still climbing, and the gravitational effects of the black hole becoming ever more apparent in the rapid motions of surrounding stars. The transition from nuclear cluster to the immediate vicinity of the black hole will represent the final stage of this journey. The arrival at the gravitational heart that anchors the trillion-star structure you have been exploring since first approaching this galaxy from intergalactic space. The light from nuclear cluster stars now surrounds you from every direction, a bath of ancient photons mixed with the younger light of those unexpected blue stars that somehow formed or arrived in this hostile environment. The combined radiation creates thermal conditions warmer than anywhere else in your voyage. The concentration of stellar energy sources heating the local environment above the cold background temperatures characteristic of most of space. This sea of light represents the accumulated output of millions of suns, all burning simultaneously within a volume smaller than the distance between our sun and its nearest stellar neighbor. The black hole draws everything toward itself through gravitational attraction that decreases with distance but never vanishes entirely, its influence extending outward through the nuclear cluster, through the bulge, through the disk and halo, reaching even beyond the galaxy's boundaries into intergalactic space, where it contributes to the ongoing approach between Andromeda and the Milky Way. This gravitational reach makes the black hole the anchor point of the entire structure, the mass concentration around which 1 trillion stars orbit in patterns that have persisted for billions of years. Your journey has been a voyage toward this anchor, a passage through the layers of structure that surround the gravitational heart. The innermost stars of the nuclear cluster become visible ahead as your approach continues, those rapid orbiters whose trajectories carry them closest to the event horizon before gravity swings them back out into the cluster population. These stars experience conditions more extreme than any others in the galaxy, gravitational time dilation slightly slowing the passage of their internal clocks compared to observers at greater distances, tidal forces stretching their structures along the lines connecting them to the central mass. They survive these conditions because the distances remain sufficient to avoid complete disruption, but the physics of their environment differs measurably from the conditions experienced by stars in the outer galaxy. The nuclear star cluster provides the final environment before the black hole itself, the last zone of stellar matter surrounding the ultimate destination of this long journey from the outer halo to the gravitational center. The passage through this cluster carries you toward the region where the black hole's presence becomes unmistakable, not through direct observation of the invisible horizon, but through the effects it produces on the space and matter around it. The innermost portion of the nuclear star cluster now surrounds your vessel, stars moving with visible speed on orbits that carry them around the central black hole in periods short enough that their motion might be detected over human observational timescales. The density of stellar light has reached its maximum. Millions of ancient and unexpectedly young suns packed into a volume where gravitational interactions happen frequently, and orbital dynamics evolve continuously through close encounters. This is the heart of the galaxy in the most literal gravitational sense, the region where the concentrated mass shapes everything and where your journey approaches its destination. The stars closest to the black hole travel at velocities approaching significant fractions of light speed, their paths bent by gravitational curvature that Einstein's general relativity describes as the warping of space-time itself around concentrated mass. At these speeds, relativistic effects become measurable, time passing slightly slower for the racing stars compared to more distant observers, lengths contracting along the direction of motion by small but real amounts. These stars inhabit a different physical regime than the slow, steady orbiters of the outer galaxy, their existence governed by the extreme physics that emerges near gravitational singularities. The event horizon of the black hole remains invisible ahead, a boundary defined by physics rather than by any material structure that could reflect or emit light for observation. Within that boundary, the gravitational curvature of space-time becomes so extreme that all directions point toward the central singularity, making escape impossible for anything, including light itself. The boundary measures perhaps several light hours across, a sphere of gravitational no return that conceals whatever lies within from any external observation. Your vessel approaches this boundary through the surrounding cluster of rapidly orbiting stars. The region between the nuclear cluster and the event horizon may contain some thin distribution of hot gas falling toward the black hole, material stripped from passing stars or accumulated from interstellar debris that wandered too close to the gravitational well. This material would heat to extreme temperatures as it spirals inward, radiating energy across the electromagnetic spectrum before crossing the event horizon and disappearing forever from the observable universe. The process happens relatively slowly for Andromeda's currently quiescent black hole, which lacks the brilliant accretion disks that characterize more actively feeding supermassive black holes in distant galaxies. Looking outward from your position near the black hole, the entire journey reverses itself in perspective. The nuclear cluster surrounding you giving way to the dense bulge beyond, which in turn surrounds the disk visible at greater distances as a flattened band of spiral structure. The halo extends beyond even the disk, its ancient scattered population occupying the outer reaches where the journey began when first approaching from intergalactic space. 1 trillion stars orbit this central point in configurations that have persisted for billions of years. The entire structure bound together by gravity, anchored at the location you now approach. The gravitational lensing effects of the black hole become apparent in observations of the region immediately surrounding the event horizon. The paths of light, bent by the intense curvature of space-time, in ways that create visual distortions of background sources. Light from stars behind the black hole curves around it, creating rings and arcs of distorted images that reveal the presence of extreme gravitational effects, even though the black hole itself emits no light. These lensing effects provide a way of observing what cannot be seen directly, the invisible mass making itself known through its influence on the light passing nearby. The final approach to the event horizon represents a boundary your vessel cannot cross and return from, a limitation imposed by physics rather than by any technical capability of the imaginary spacecraft carrying you on this journey. The event horizon marks the point where the escape velocity equals the speed of light, where no amount of acceleration could ever restore motion toward the external universe once that boundary has been crossed. Whatever enters the black hole remains there forever, adding to its mass and angular momentum without ever returning information to outside observers. The stars racing around the black hole on their rapid orbits pass through the region immediately surrounding the event horizon without being captured, their velocities sufficient to maintain elliptical paths that carry them close to the boundary before swinging back out into the nuclear cluster. These stars experience the most extreme conditions of any objects in the galaxy. Gravitational time dilation, causing measurable differences in the passage of time between their locations and more distant reference points. An observer on such a star would see the external universe evolving slightly faster, the accumulated effect of time passing differently at different gravitational depths. The black hole has likely existed since early in the galaxy's history, forming either from the direct collapse of an enormous primordial gas cloud or through the gradual merger of smaller black holes that grew from the deaths of early massive stars. Supermassive black holes are found at the centers of essentially all large galaxies, suggesting that their formation is a natural consequence of the processes that create galactic structure. Andromeda's central black hole grew to its current mass over billions of years, consuming material that fell toward it while growing through mergers with the black holes of smaller galaxies that Andromeda absorbed throughout its history. The journey from the outer halo to this innermost region has covered perhaps 100,000 light-years of structure, from the ancient scattered stars of the halo through the globular cluster and spiral arms and bulge to this nuclear concentration surrounding the gravitational heart. Each region offered its own characteristics and experiences, the variety of the galaxy revealing itself through the progression inward toward this central point. The destination now lies immediately ahead, as close as any approach can reach without crossing the boundary from which nothing returns. The destination has been reached in the sense that further approach becomes meaningless beyond a certain point. The black hole, hiding its interior from any observation and representing the end of explorable space within this galaxy. The event horizon ahead marks the ultimate boundary the edge of the observable universe as defined by the physics of extreme gravitational curvature. Your vessel holds position at the closest approach that permits eventual departure, observing the gravitational heart of Andromeda from as near as safely possible. The nuclear cluster continues its ancient dance around this central point, millions of stars pursuing their rapid orbits, while the black hole sits silently at the center, growing slowly through the consumption of whatever material falls within its gravitational grasp. This configuration will persist for billions of years into the future, the galaxy maintaining its structure while slowly evolving through the processes that have shaped it since its formation over 10 billion years in the past. The journey finds its completion here, at the center of Andromeda, the supermassive black hole, anchoring everything you have explored since first approaching this galaxy across the emptiness of intergalactic space. The event horizon lies ahead, invisible itself, but revealed through its effects on the surrounding starlight that bends and distorts as it passes through the extreme gravitational curvature. The nuclear star cluster surrounds this central point with its millions of rapidly orbiting suns. The bulge extends beyond that. The disk and halo reach still further outward in the structure that houses 1 trillion stars. This is the destination, the gravitational heart, the anchor point of an entire galaxy. The black hole contains perhaps 100 million to 230 million times the mass of our Sun, compressed into a region from which not even light can escape, hidden behind an event horizon that marks the boundary between the observable universe and whatever lies within. This mass represents a significant fraction of the galaxy's total content, concentrated at a single point that influences everything else through gravitational attraction, reaching outward across 100,000 light years and beyond. The merger of Andromeda with the Milky Way in several billion years will likely combine their central black holes into an even larger object, the gravitational hearts of 2 galaxies uniting just as their stellar populations intermingle. Looking outward from this central position, the full extent of the structure you traversed reveals itself in concentric layers of different character surrounding this anchor point. The nuclear cluster glows most brilliantly, with its concentration of ancient and young stars pursuing rapid orbits around the central mass. The bulge extends beyond, that spheroidal distribution of ancient populations that marked your passage through the inner galaxy. The disk spreads at greater distances still, its spiral arms visible from this perspective as curving bands of light and dark winding around the central regions. The halo occupies the outermost volume, sparse ancient stars scattered across a vast sphere that marks the galaxy's gravitational boundary with intergalactic space. Each of these regions provided its own experience during your voyage inward, the variety of galactic structure revealing itself through the progression from sparse to dense, from ancient uniformity to active variety, and back to ancient uniformity again at different scales. The halo's scattered wanderers, the globular cluster's dense ancient population, the spiral arm's active star formation, the interarm's quiet older stars, the bulge's uniform ancient sea, the nuclear cluster's extreme concentration. Each environment contributed to the complete picture of what this galaxy contains and how its structure organizes the trillion stars that call it home. The gravitational influence of the black hole extends beyond even the visible structure of the galaxy, reaching outward to affect the motion of anything within millions of light years. This influence contributes to the ongoing approach between Andromeda and the Milky Way, the two galaxies falling toward each other at over 100 kilometers per second as their mutual gravity overcomes the expansion of space between them. The collision will unfold over hundreds of millions of years, stars from both galaxies intermingling, while both central black holes spiral toward eventual merger. The far future will see a single combined galaxy where Andromeda and the Milky Way once existed as separate structures. The stars surrounding the black hole continue their rapid orbits, as they have for billions of years, tracing paths determined by the gravitational curvature of space-time around this concentrated mass. Some of these stars have orbited millions of times since their formation, while others, on more distant paths, have completed only thousands of circuits. The orbital dance continues without any awareness among the participants of the role they play in this cosmic structure, each star simply following the path dictated by physics and initial conditions set during its formation long ago. The journey from intergalactic space to this central point covered perhaps 100,000 light-years of distance. Though the experience compressed this voyage into the timescale of a single night's rest, wherever you are actually located while listening to these words. The real Andromeda exists right now at the position in the sky where ancient astronomers first noticed its fuzzy glow without understanding what it represented. A neighboring galaxy, 2.5 million light-years distant, that we observe through light that departed before modern humans existed. The structure described throughout this voyage reflects what astronomers have learned about that distant island of stars through centuries of observation and analysis. The return journey would carry you back through all the same environments in reverse. The nuclear cluster giving way to the bulge to the disk to the halo, and the halo finally to the intergalactic void that separates Andromeda from home. The Milky Way waits at the end of that return crossing, a spiral galaxy remarkably similar to Andromeda in structure and content, containing perhaps 400 billion stars, including the one that warms the planet where you rest tonight. The similarities between the two galaxies make Andromeda the best laboratory for understanding our own home, close enough to study in detail, while far enough to observe as an external structure. The experience of this voyage has carried you through environments no human has ever directly witnessed. Places that exist right now exactly as described, but that lie far beyond any possibility of physical travel, given the limitations of physics as we understand it. The journey belongs to imagination informed by science, speculation grounded in observation, a voyage of the mind through spaces that the mind can comprehend even when the body cannot visit. The galaxy you have explored is real, its structure accurate to the best of current understanding, its destination genuinely anchoring 1 trillion stars in gravitational embrace. The darkness surrounding the black hole's event horizon represents the end of this particular exploration, the boundary beyond which travel becomes permanently one-directional and from which no return journey would be possible. Your vessel holds position at the closest safe approach, observing the gravitational heart from the minimum distance that permits eventual departure through the layers of structure extending outward toward intergalactic space. The destination has been reached, the center of Andromeda witnessed as closely as observation allows. The journey complete, after traversing an entire galaxy from its outermost reaches to its gravitational core. The trillion stars of this galaxy continue their orbits as they have for billions of years, unaware of your passage and unchanged by your observation. Each one, a sun burning through its fuel, while gravity maintains the structure that has persisted since the galaxy formed over 10 billion years ago. The spiral arms will continue triggering star formation. The bulge will continue housing its ancient populations. The nuclear cluster will continue surrounding the black hole that anchors everything in gravitational embrace. The galaxy will persist for billions of years more, eventually merging with the Milky Way in a collision that will reshape both structures into something new. The night sky above, wherever you rest, contains this galaxy as a fuzzy patch of light, visible on dark, clear evenings, a destination that exists right now as the stars that compose it continue burning across 2.5 million light-years of separation. The light arriving tonight departed during the age when human ancestors first walked upright, carrying information about conditions that have since changed in ways we cannot yet observe. The Andromeda you have explored represents that ancient state, a snapshot of a galaxy as it existed before our species emerged to wonder about the lights in the sky. The voyage concludes here at the center, the black hole ahead marking the final boundary of this exploration through a neighboring galaxy. The journey from intergalactic void to gravitational heart has revealed the structure of Andromeda layer by layer, each region contributing its character to the complete picture of what this trillion-star island contains. The experience belongs to the night, to the quiet hours when curiosity and rest coexist, when the mind can travel while the body remains still. The galaxy waits in the darkness, patient and unchanging, ready for another voyage whenever wakefulness permits another journey among the stars.